problems are my solutions to them that go along with the first, second laws of thermodynamics, I guess the zeroth law also. So I want to go through some of these things. So basically, problem 4 was looking at converting potential energy into a power plant. And so I want to make sure I actually have these open. I did them, but I want to make sure I actually have them open to the pages that I need. So hold on a sec. Okay, so basically it says the Glen Canyon hydroelectric power plant releases 690 cubic meters of water per second, which is a lot, by the way. I think that's a lot of cubic feet. Basically, it's released 220 meters below the top of the dam. The generators are 90% efficient. What's the maximum possible electric power? So first of all, you should remember, hopefully from our density things, that water has a density of 1,000 kilograms per cubic meter. And then you multiply that. Basically, you're getting the MGH, which is the potential energy of the water. And that's 1.52 times 10 to the 9th joules per second. That's converted from PE and would be converted into kinetic energy. But it says only 90% of that is actually converted to electric energy. So multiply by 0.9, get 1.37 billion joules per second, or 1.37 billion watts. The common unit of power for electric generation for power plants is a megawatt, so that's 1,370 megawatts. So for problem number 5, it says if an individual white LED has an efficiency of 20%, it uses 1 watt of electric power. How many LEDs combined would give a total of 1.6 watts of visible light output? So if it's 20% efficient and it uses 1 watt of electric power, that means each bulb produces 0.2 watts of visible light output. So 0.2 watts times X number of bulbs equals 1.6 watts of visible light output. So that's 8 bulbs. It's pretty easy. Problem 32 ended up being where it says your roommate leaves a 120 watt fan running in your apartment. Over the course of an hour, how much thermal energy does the fan add to the air? It's interesting to think about this because you think of a fan as a cooling thing, and it can cool you, but because it's basically converting electrical energy into mechanical energy and there's some heat waste, this basically is ending up adding 120 joules per second of energy to the air. So times 3,600 seconds in an hour, that's 432,000 joules. So essentially the fan will warm up the room. However, what ends up happening is when air blows over your skin, assuming the humidity is not super, super high, and you perspire, then essentially as you're perspiring, that liquid goes from a liquid form, or that liquid sweat or perspiration goes from liquid form to a gas form. And as it does that, as the molecules convert from a liquid to a gas, basically that takes energy. And so it pulls thermal energy from your body to do that. And so essentially it does make you feel cooler when you have air going over you. And it's a legitimate physical process. It's not that you're feeling cooler. You will actually be cooled down. That's the process of sweating does that. For problem 33, 600 joules of heat energy transferred to a system that does 400 joules of work. How much does the system's thermal energy change? So this is pretty easy. 600 joules in, 400 joules out. So you have a gain of 200 joules, so plus 200 joules. For problem 34, it says compressing air to fill a scuba tank warms it up. So expanding of a gas cools it down. Compressing it warms it up. So dive shot compensates of this by putting the tank in a tub of water, which is basically like a cold sink, keeping the tank and the gas inside at a constant temperature as it's filled. So if the system is the tank, what are the signs of W and Q, and what's the magnitude? So because the air is being compressed inside the tank, then work is being done to the tank and the air inside of it. And so work is positive. And because the temperature stays the same, the thermal energy, or delta U, is 0. So therefore the Q, or the heat, has to be transferred out of the tank. And that would be negative, and the same magnitude as work is positive. So that goes through that equation, which I've shown a couple times also. Okay, for problem 35, it's asking if 10 joules of heat are removed from a gas sample, while it's being compressed by a piston that does 20 joules of work. What's the change in thermal energy of the gas? Well, so you have 20 joules of work being done, but 10 joules of heat being removed. So Q is negative 10, W is plus 20. So plus 10 joules is the change of thermal energy, and therefore, since the change in thermal energy is positive, the temperature will increase. 39, I screwed up. Yikes. Apparently, I do not read properly because 39 said that the cold temperature reservoir is 20 degrees Celsius. The hot temperature one is 600 Celsius. Apparently, I thought it said 200 Celsius. Okay, so maybe I was looking at the 20 and I don't know what I ended up doing. However, 600 Celsius is 873 Kelvin. Cold 20 Celsius is 293 Kelvin. So essentially here then this question is asking, says how if it is a 30% of the maximum possible efficiency, how much energy does this engine extract from the hot reservoir to do 1,000 joules of work? So 1,000 joules of work is what you get out, but you basically need to find the efficiency of this system. So using the laws of thermodynamics in this 1 minus Tc over Th, when I corrected for that, I get that the maximum possible efficiency is 66.4%. However, it says it only extracts 30% of the maximum possible efficiency, so 0.664 times 0.30 gives me 19.9%, might round to 20%. So then 1,000 joules is what you get, and what you pay is the amount that you're trying to find, and it's 20% efficient, so it's 5 times that, 5,000 joules. Hi, Mr. Lighty, doing a screencast. It's okay. Have a good evening. Take care. So I got 5,000 joules, 5,020 joules, something like that. That's Mr. Lighty. He's a really good guy. Number 43, each second, says a nuclear power plant generates 2,000 megajoules of thermal energy from the nuclear reactions. The energy is used to boil water, produce high-pressure steam at 300 Celsius. The steam spins a turbine, which produces 700 megajoules of electric power. The steam is condensed. Water is cooled to 30 degrees Celsius before starting the cycle again. What's the maximum possible efficiency of the plant? So here, cold temperatures, 30 Celsius, that's 303 Kelvin. Hot temperatures, 300 Celsius, that's 573 Kelvin. So the maximum theoretical efficiency is 47%. Here you get 700 megawatts out of 2,000 that are put in. That's 35%. That's pretty good. That's actually very good. I'm kind of a pro-nuclear power person, but I think it does have to be done differently to make it make sense in the United States. Right now it does not make sense with how we build them. Okay, for problem 52, there are a bunch of pictures up here, and it's saying which, if any, of the heat engines violate A, the first law of thermodynamics, or B, the second law of thermodynamics explained. So first law of thermodynamics says you get out more than you put in. So in this particular case, for A, 50 joules are put in, it says 30 and 20 come out, so it does not violate the first law of thermodynamics. Also, for all these heat engines, the hot temperature is 600 Kelvin, the cold temperature is 300 Kelvin. So because of that, the maximum possible efficiency, according to the second law of thermodynamics, is 50%. However, here you get 30 joules out for putting 50 joules in. That's 60%, so this does violate the second law. You can't be more efficient than the maximum efficiency. And why is that the maximum? Well, if the temperature is off by 50%, then the energy in each area has to be different by 50%. But it's not. It goes down by 60%. Mr. Lighty gave me a good message, which is saying the curb is slippery. Thanks, Mr. Lighty. For B, I have 10 joules in, 4 and 7 here. I have 11 joules out. Well, that's easy. That violates the first law of thermodynamics. So you cannot get out more than you put in. For this third one, which is letter C, 30 joules in, 10 joules out, 20 joules down here, doesn't violate the first law because what comes out is what goes in. The efficiency that you actually have is 10 over 30, that's 33.3%. That doesn't violate the second law either because the maximum efficiency is still 50%. So that one's okay. For problem 64, this is basically asking if you have a heat engine doing 10 joules of work and exhausting 15 joules of waste. What's the engine's efficiency? So that means if you have that total output, that's 25 joules, so that's your input. So you get 10 joules of work done, 25 joules put in, that's a 40% efficiency, what you get over what you pay. And the cold reservoir temperature is 20 degrees Celsius. What's the minimum possible temperature in degrees Celsius at the hot reservoir? So I got to convert to Kelvin. So 40% efficient is equal to 1 minus 293 over TH. So essentially I move this over, I get negative 0.6 equals negative 293 over TH. Make those both positive. But overall, that ends up being a total of 488 Kelvin. Well, I'll subtract 273 Kelvin is equal to 0 Celsius, and that's 215 degrees Celsius. So that's the minimum hot temperature that you can have to be this efficient. Problem 66. Says an engineer claims to have measured the characteristics of a heat engine that takes in 100 joules of thermal energy and produces 50 joules of useful work. Is the engine possible? Yeah, you can get out 50 joules of useful work from putting in 100 joules of thermal energy, but that means that only 50 joules will go from to the cold reservoir, and you had 100 joules of energy coming from the hot reservoir. So therefore, the ratio of temperatures, hot to cold, would have to be greater than or equal to 2 to 1. So something like that. Yep. Okay. Hopefully these help, and hopefully this chapter is making some sense now.